See, there are times they would give you family of curves. They would give you family of curves. Say, a family of curves essentially could be, say, a function of x, y, and an arbitrary constant. Different values of c will give me different members of the family. Different values of c will give me different members of the family. F of x, y, z equal to 0 is a family of curves. Is a family of curves, right? Where c is an arbitrary constant. Different values assigned to c will give me different members of this family, right? C is an arbitrary constant. Now, what I want to do is, I want to find another family of curves. Say this is a family of curves. F of x, y, c equal to constant is family of curves. So this could be c equal to 1, c equal to 2, 3, 4, etc. Different values assigned to c, giving me different members of this family. This is f of x, y, c equal to 0, say. Family of curves. And I want to find, so this is my family 1. This is family 1. And I want to find family 2. I want to find family 2, which is phi of x, y, and some c. Obviously, it's an arbitrary constant. Don't think that this c and this c are equal. They're parameters. Phi of x, y, c equal to 0. Different values of c giving me different members of this new family 2. Some other family. In a manner that if you take any member of this family, phi x, y, c equal to 0, then it cuts every member of family 1. If you take any member of family 2, it cuts every member of family 1 orthogonally. What that means is, see, that means this is a member of family 2. This is a member of family 2. And this is a member of family 1. When I say that this curve cuts this curve orthogonally, what it means is the tangent to one curve at the point of intersection is perpendicular to the tangent to the other curve at the point of intersection. The angle between the tangents at the point where they intersect is 90 degrees. This curve and this curve, that's also orthogonal. That means tangent to this curve and tangent to this curve, they enclose an angle 90 degrees. Tangent to this curve, that's 90 degrees. So this curve, which is a member of family 2, intersects every other curve of 1, every other member of curve 1 perpendicularly means orthogonally. That means, then this curve, this family of curves is said to be an orthogonal family, These two curves are said to be orthogonal to each other, You know what I'm saying? What it really means is, say at the point where they intersect, say P is a point xy, where this member is intersecting this member. What it means is, the slope of the tangent to this curve, dy dx, to curve at xy, and the dy dx to this curve at xy, the product of these two dy dx's will be minus 1. The product of the dy dx to this curve at this point and dy dx to this curve at this point will be minus 1. Product of the slopes of the tangents at the point where they intersect would be minus 1. That's when the curves intersect orthogonally. Right? What it also means is, the tangent to one curve is like a normal to the other curve. The tangent to one curve is like a normal to the other curve, isn't it? See, this is the tangent to this curve. Look at this curve. this is the tangent. Its normal will be a line perpendicular to it, which is this line, which is a tangent to this curve. That means the tangent to one curve is the normal to the other curve. This is what it means. That's when they are said to intersect each other orthogonally, right? Have you seen that somewhere? These could be electric lines of force, these could be electric lines of force, and these would be equipotential surfaces, isn't it? A family of curves that are electric lines of force, another family of curves that are equipotential lines. And every member of one intersects the other one orthogonally, isn't it? Electric lines of force and equipotential lines will intersect normally, right? I mean, for example, you know, somebody gave you the electric lines of force in the xy plane, right? Somebody gave you the electric lines of force in the xy plane. And electric lines of force are a family of curves. It's not one curve. They are a family of curves, right? Say xy equal to c is a set of electric lines of force where c is a parameter. C is a parameter. It's not a fixed constant. It's not a fixed constant. It's an arbitrary constant. Different values of c will give me different electric lines of force. Different values of c will give me different electric lines of force. Yes or no? Now, I want to be able to find the equipotential lines. In this region, given the electric lines of force, I want to find the equipotential. C is an arbitrary constant, not a fixed constant. C is given a specific value, it will give me equation of one electric line of force. But if C is an arbitrary constant, it will give me family of electric lines of force, right? C in this case is an arbitrary constant, giving me the various electric lines of force in this region, giving me various electric lines of force in this region, right? Now, I want to find the differential equation. I want to find the differential equation that represents this family of curves. I want to find the differential equation that represents this family of curves. Now, one, how many arbitrary constants in this equation? One. What would be the order of the differential equation? One. So how many times do you want to differentiate? Only once. Very clearly, and you want to eliminate C. You want to eliminate C. C will appear only in the primitive, in the solution to the differential equation. The differential equation will not talk of C at all, right? So I want to differentiate with respect to x1, say. Get rid of C, giving me the differential equation whose primitive or whose solution is this family of curves, which is, let's say, could be physically electric lines of force in the xy plane created out of a charge distribution, right? So when I differentiate this with respect to x, I get y plus x dy dx equal to 0. Good. This is the differential equation. This is the differential equation. Yes or no? Now I want to find the differential equation for an equipotential line in this region. For an equipotential line in this region, right? All electric lines of force will subscribe to this condition. All electric lines of force will subscribe to this condition, right? Now, look, if this is a sample electric line of force in this region, if this is a sample electric line of force in this region, and this is an equipotential line in the same region, if this is the equipotential line in the same region, then what would dy dx, this is dy dx, this is the point P, x comma y, right? Right? What's dy dx for the electric line of force? The dy dx for the electric line of force at this point is minus y by x, right? But this electric line of force, the tangent to the electric line of force, is really a normal to the equipotential line. The tangent to the electric line of force will really be a normal to the equipotential line. And the slope of the normal is what? Slope of the normal is minus dx dy. I repeat, dy dx, which is slope of the tangent to the electric line of force will be at x comma y will be the slope of the normal to the equipotential line at xy, right? So what does this dy dx represent? Slope of the tangent to the electric line of force, which will also be the slope of the normal to the equipotential line, right? This is the slope of the normal to the equipotential line. This is slope of the normal to the equipotential line. Are you all there with me on this? समझ में आया ना? This is the slope of the normal at x comma y to the equipotential line. So slope of the tangent to the equipotential line, potential line is going to be what? Minus dx dy. This is the slope of the normal. Slope of the tangent therefore will be minus dx dy. Yes or no? Are you all there with me? Now, so the equation of this is what? Y plus x into slope of the equipotential, slope of the electric line of force equal to 0, right? Y plus x, slope of the electric line of force equal to 0. M is dy dx, slope of the electric line of force. But y plus x, slope of the electric line of force would be negative of the slope of the negative of 1 by slope of the equipotential line. Yes or no? Slope of the electric line of force would be minus 1 by the slope of the equipotential line. That equal to 0, yes or no? Right? But slope of the equipotential line would be the dy dx for the equipotential line would be the dy dx for the equipotential line. That means y plus x into minus 1 by this dy dx is the slope of the equipotential line. This dy dx is the slope of the equipotential line at x comma y. That's equal to 0. Yes or no? So when I solve this equation, this y in terms of x will give me the equipotential line. At x comma y, this is the condition enjoyed by the equipotential line. So when I solve this equation, that means dy dx replaced by minus 1 by dy dx, dy dx in this family of curves replaced by minus 1 by dy dx. When I solve this differential equation, what would it give me? It will give me family of orthogonal curves. It will give me family of equipotential lines. When I solve this equation, it will give me family of equipotential lines. That means in a very general sense, if I have dy dx and I replace dy dx by minus 1 by dy dx and I solve that differential equation, then I get family of orthogonal curves. If in any curve, let's say first order curve, this is a first order curve, one arbitrary constant, right? If I replace dy dx by minus 1 by y dy dx and solve that differential equation, what would I get? Family of orthogonal curves. Replacing dy dx by minus 1 by dy dx will give me family of orthogonal curves. Yes or no? Wherever dy dx appears, replace that by minus 1 by dy dx. Solve the new differential equation. The solution to the new differential equation will give me family of orthogonal curves. In this case, if this represented electric lines of force, then this differential equation will represent equipotential lines. If these were representative of electric lines of force, this differential equation would be equipotential lines. Yes or no? Got me? Make sense now? So let's solve this and see what happens. So I'm trying to find curves orthogonal to these curves. I'm trying to find curves orthogonal to these curves. So y minus x dx dy equal to 0. See, y minus x dx dy equal to 0. Right? This will give me y dy minus x dx equal to 0. Right? Y dy minus x dx equal to 0. When I integrate, I get y squared by 2 minus x squared by 2 equal to a constant. So multiply by 2, it will still be a constant. Where c is an arbitrary constant, not a fixed constant, it's an arbitrary constant. So if I assign different values to c, I get different members of the curve, and every member of this curve will be orthogonal to every member of this curve. So this is family of orthogonal curves. This is family of orthogonal curves. Yes or no? Right? So all that you need to do is, given a family of first order curves, f of x, y, c equal to 0, find the differential equation to this family. The differential equation to this family would be, say, some h of x, y, and only first order derivative will be involved because there is only one arbitrary constant. This will be the form of the, if you eliminate, see, it will be a function of x, y, and dy dx equal to 0. Isn't it? That will be the formation of the differential equation to this family of curves. And then what you do is, if you replace this dy dx by minus dx dy, replace this dy dx by minus dx dy, then the new family would be family of orthogonal curves. So the family of orthogonal curves is obtained by replacing this by minus dx dy. In this differential equation, replace dy dx by minus dx dy and solve the new differential equation. That will give you family of orthogonal curves. Yes or no? Are you all okay with this? Right?